Today we're going to talk about something called continuity. Start with the definition. A function f is continuous at x equals c if and only if. That's what this little symbol means, IFF. It's not a typo. A function is continuous at x equals c if and only if there are three conditions. Condition number one, f of c must exist. A function can only be continuous at a point if you can find the output value of that function at that point. That's step number one. So to show you what that means, we've got a point, an x value, c. For the function to exist, there must be an f value at c. Okay, great. And the limit as x approaches c must exist. I should say the limit of f of x as x approaches c must exist. So there has to be some value that the function is getting closer and closer and closer to as x approaches c. So that appears to be this. And number three, that limit of f of x, I should say, as x approaches c, has to equal the same thing as the actual output value, f of c, which is not what I have drawn there, so I need to adjust my drawing to match that. So now I have a continuous function here. Sorry, move all these up to be in the same place. This is a continuous function because f of c exists, that's that dot, and the limit of f of x as x approaches c exists. We're getting closer and closer to the same thing from both sides, and they happen to be in the same place. Okay. When you're asked about continuity, you need to check all three of those definitions. So you will be asked questions. Is this function continuous at x equals 2? And your job is to check all three of those. Does f of 2 exist? Does the limit of f of x as x approaches 2 equal anything? Meaning, is it the same from both sides? And are those two things equal to each other? Okay, so that's our first definition. The next definition is continuity on an interval. A function f is continuous on the open interval from a to b as long as f is continuous at every x equals c where c is between a and b. So to give you an example of a function that is continuous on an open interval, I can draw a function, here let's put a and b on the x-axis here. I can draw a function that, even though it might not be continuous at the point x equals b, is continuous everywhere between a and b. So let's put a vertical asymptote there. This is a function that is continuous on the open interval from a to b, because for every point in between a and b, even though it's not including a and b, the function is continuous. Okay. That, to be honest, doesn't come up that often. Our next one is a little bit more technical. A function is continuous on a closed interval from a to b. Notice the notation here, which you'll get very familiar with this year. That bracket means we include a and we include b. We call that a closed interval. A function is continuous on the closed interval from a to b if, first of all, f is continuous on the open interval from a to b. So that's the first step. And we also have to make sure that the function is continuous at the point a, but the tricky part to this is it only has to be continuous from one side. So what we'll check is to make sure that the limit of f of x as x approaches a from the right is equal to f of a. and the limit of f of x as x approaches b from the left is equal to f of b. So let me draw an example of this for you, why this technical definition matters. Let's say we have a function here with a and b. We could draw a function that is continuous on the closed interval from a to b, even though the function, the entire thing, we wouldn't say the function is continuous at the point a. Let's say it has what's called a discontinuity there. So this is an example of a function that doesn't look like it's continuous at a, but it is continuous on the closed interval from a to b, because the limit as x approaches a from the right is the same thing as f of a. And then one more little definition here. We say that a function has what's called a removable discontinuity, which you also have learned in the past is called a hole. You learned about those when you graphed rational functions in Algebra 2, when things cancel out. And there's still a hole from a domain restriction. The technical way we would say there's a removable discontinuity is if the limit of f of x as x approaches c exists, but the limit of f of x as x approaches c does not equal f of c, which could happen if, let's just put a point c there, so we've got the limit from both sides, the function is approaching the same thing, but there is no f of c there. Or could be an f of c, but it could be somewhere else, like that. This is an example of a function with a removable discontinuity. This little dot does not need to be there, but it can be there. And then the last kind of discontinuity, the second kind is what we call a jump discontinuity. And that would be if there's a limit from both sides, but it's not the same. So the limit of f of x as x approaches c from the left exists, so there has to be a limit here. And there has to be a limit from the other side. The limit of f of x as x approaches c from the right exists, but they do not equal each other. From the left does not equal the limit of f of x as x approaches c from the right. For example, a function which exists from the exists from the right, exists from the left, but isn't coming to the same place. That's what we call a step discontinuity or a jump discontinuity. Okay, there's a third kind of discontinuity we'll talk about in another class.